In the cosmic theater of existence, Earth emerges as a protagonist with an epic tale spanning billions of years. Picture a primordial chaos, where molten seas roiled beneath turbulent skies, and continents danced in a celestial ballet of collisions and separations. From these tumultuous beginnings, a symphony of geological forces orchestrated the sculpting of our planet's surface, carving mighty mountain ranges, etching deep valleys, and weaving intricate networks of rivers and oceans. As eons passed, the stage was set for the emergence of life itself. In the gentle cradle of Earth's oceans, the first stirrings of biological complexity began to take shape. Simple cells gave way to multicellular organisms, and the dance of evolution quickened its pace. From the murky depths of ancient seas to the verdant forests of distant epochs, life spread and diversified, exploring every niche and corner of our planet with relentless ingenuity. But Earth's story is not just one of growth and abundance. It is also a saga of cataclysm and renewal. Mass extinctions, sparked by cosmic impacts or volcanic upheavals, served as harrowing punctuation marks in the narrative of life. Yet, from the ashes of devastation, new forms of life emerged, resilient and adaptive, driving the endless cycle of evolution ever forward. As we stand amidst the wonders of the modern world, it's easy to forget the epic journey that brought us here. But by delving into the annals of Earth's history, we gain a deeper appreciation for the beauty and complexity of our planet, and perhaps catch a fleeting glimpse of our place within the grand tapestry of the cosmos. So let us embark on this odyssey together, as we unravel the mysteries of Earth's past and contemplate the boundless possibilities of Titan's future.
Life, living matter, and, as such, matter that shows certain attributes that include responsiveness, growth, metabolism, energy transformation, and reproduction. Although a noun, as with other defined entities, the word life might be better cast as a verb to reflect its essential status as a process. Life comprises individuals, living beings, assignable to groups. Each individual is composed of one or more minimal living units, called cells, and is capable of transformation of carbon-based and other compounds known as metabolism, growth, and participation in reproductive acts. Life forms present on Earth today have evolved from ancient common ancestors through the generation of hereditary variation and natural selection. Although some studies state that life may have begun as early as 4.1 billion years ago, it can be traced to fossils dated to 3.5 to 3.7 billion years ago, which is still only slightly younger than Earth, which gravitationally accreted into a planet about 4.5 billion years ago. But this is life as a whole. More than 99.9% of species that have ever lived are extinct. Earth formed around 4.54 billion years ago, approximately one-third the age of the universe, by accretion from the solar nebula. Volcanic outgassing probably created the primordial atmosphere and then the ocean, but the early atmosphere contained almost no oxygen. Much of the Earth was molten because of frequent collisions with other bodies which led to extreme volcanism. While the Earth was in its earliest stage, a giant impact collision with a planet-sized body named Theia is thought to have formed the Moon. Over time, the Earth cooled, causing the formation of a solid crust, and allowing liquid water on the surface. In June 2023, scientists reported evidence that the planet Earth may have formed in just 3 million years, much faster than the 10 to 100 million years thought earlier. Recognizable humans emerged at most 2 million years ago, a vanishingly small period on the geological scale. The earliest undisputed evidence of life on Earth dates at least from 3.5 billion years ago, during the Eoarchean era. The standard model for the formation of the solar system, including the Earth, is the solar nebula hypothesis. In this model, the solar system formed from a large, rotating cloud of interstellar dust and gas called the solar nebula. It was composed of hydrogen and helium created shortly after the Big Bang 13.8 billion years ago and heavier elements ejected by supernovae. The solar wind of the newly formed T Tauri star cleared out most of the material in the disk that had not already condensed into larger bodies. The same process is expected to produce accretion disks around virtually all newly forming stars in the universe, some of which yield planets. You're probably fed up with the constant day-to-day experience and interaction with Earth and earthly creatures. Wonder where else life could thrive on inside our solar system. Somewhere far from home that you can call home. Let's take a deep dive into Titan, Saturn's largest moon.
Welcome to the enigmatic realm of Titan, Saturn's largest moon, a celestial marvel shrouded in mystery and draped in intrigue. Imagine a world where rivers flow not with water, but with liquid methane and ethane, where towering mountains pierce through a thick haze, and where vast plains stretch as far as the eye can see. Titan beckons explorers with its tantalizing secrets, offering a glimpse into a realm where the familiar dance of geology and chemistry takes on an otherworldly twist. Step foot onto Titan's surface and you'll find yourself immersed in a landscape that defies expectation and challenges the imagination. Beneath its hazy veil lies a world teeming with geological wonders, from cryovolcanoes that spew icy plumes to hydrocarbon lakes that shimmer in the alien light. Here, the very essence of life as we know it takes on a new form, as complex organic molecules dance amidst the ethereal mist, hinting at the possibility of a prebiotic world waiting to be explored. But Titan is more than just a distant curiosity, it's a scientific frontier ripe for discovery. Through the lens of spacecraft like NASA's Cassini and ESA's Huygens probe, we've glimpsed the wonders of this distant moon, unlocking secrets that challenge our understanding of planetary evolution and the potential for life beyond Earth. And as we set our sights on future missions, the allure of Titan only grows stronger, promising new revelations and adventures yet to come. So join us as we embark on a journey to Titan, where the mysteries of the cosmos collide with the boundless curiosity of the human spirit. Together, let's unravel the vibrant tapestry of this alien world and unlock the secrets that lie hidden beneath its icy surface. Welcome to Titan, where the wonders of Saturn's realm await.
Titan, the largest moon of Saturn and the only moon in the solar system known to have clouds and a dense atmosphere. It is the only body other than Earth that is known to currently have liquid on its surface. It was discovered telescopically in 1655 by the Dutch scientist Christian Huygens, the first planetary satellite to be discovered after the 4 Galilean moons of Jupiter. The moon is named for the Titans of Greek mythology, which include Cronus, equated with the Roman god Saturn and his 11 siblings. In an Earth-based telescope, Titan appears as a nearly featureless brownish-red globe, its surface permanently veiled by a thick haze. It is larger than the planet Mercury and more massive than Pluto, and, in significant ways, it resembles a planet more than it does a typical moon. Titan orbits Saturn at a mean distance of 1,221,850 kilometers, 759,220 miles, taking 15.94 Earth days for one revolution. It rotates once on its axis for each revolution, that is, its rotation is synchronous so that it always keeps the same face towards Saturn and always leads with the same face in its orbit. The diameter of the solid body of Titan is 5,150 kilometers, only about 120 kilometers less than that of Jupiter's moon Ganymede, the largest moon in the solar system. If its hundreds of kilometers of atmosphere are included, however, Titan far exceeds Ganymede in size. Titan's relatively low mean density of 1.88 grams per cubic centimeter implies that its interior is a mixture of rocky and icy materials, the latter probably including ammonia mixed with water and methane and possibly including liquid layers, covered by a solid, mostly water ice crust. A rocky core may lie at the center and extend to perhaps 80% of the total radius. In its bulk properties, Titan resembles other large icy moons of the outer solar system, such as Jupiter's Ganymede and Callisto and Neptune's largest moon, Triton. Composition of atmosphere. Titan's atmosphere was first detected spectroscopically in 1944 by the Dutch-American astronomer Gerard P. Kuiper, who found evidence of the absorption of sunlight by methane. However, studies of the refraction of radio waves in the atmosphere carried out during Voyager 1's flyby in 1980 showed that methane molecules must make up only a few percent of the total number of molecules in the atmosphere and that the predominant molecules are not detectable in visible light spectra. Comparison of infrared and radio data from Voyager revealed that the atoms and molecules making up the atmosphere have a mean molecular weight of 28.6 atomic mass units. Thus, Voyager correctly identified the most plausible major constituent to be molecular nitrogen, although some atomic argon could also be present. Other constituents detected by Voyager in Titan's atmosphere via their absorption of ultraviolet light from the Sun were molecular hydrogen and many carbon-bearing molecules, believed to be produced by solar ultraviolet light acting on methane and nitrogen at high altitudes. These include carbon monoxide, carbon dioxide, and the organic gases ethane, propane, acetylene, ethylene, hydrogen cyanide, diacetylene, methylacetylene, cyanoacetylene, and cyanogen, all observed in trace amounts. Structure. Titan's atmosphere is similar to Earth's both in the predominance of nitrogen gas and in surface pressure, which is about 1.5 bars, or 50% higher than sea level pressure on Earth. Titan's atmosphere is much colder, however, having a temperature at the surface of -179 degrees Celsius, and it contains no free oxygen. A troposphere analogous to Earth's extends from Titan's surface to an altitude of 42 kilometers, where a minimum temperature of -202 degrees Celsius is reached. Clouds of nitrogen are not present, apparently because temperatures are always above the condensation point of nitrogen. Initial data from the Cassini-Huygens spacecraft, which began exploring the Saturnian system in 2004, show that methane is indeed a minor atmospheric constituent but a very important one, possibly playing a role analogous to that of water vapor in Earth's troposphere. Near Titan's surface, about 5% of the atmospheric molecules are methane, the fraction decreasing with altitude. For comparison, Earth's lower atmosphere contains about 1% water vapor on average. When Cassini first encountered Titan, it observed a large outburst of methane cumulus clouds over Titan's south polar region. Later in the mission, a much larger system of clouds was discovered over the north polar region. Smaller, more transient clouds have been observed in the temperate zones. There is indirect evidence that methane, rain, occasionally precipitates near the surface. Titan has a thin atmospheric layer of roughly constant temperature above the troposphere, followed by an extensive stratosphere ranging from 50 to 200 kilometers in altitude, where temperatures steadily increase with altitude. Titan's haze. Titan's veiling haze is probably composed of an aerosol of complex organic solids that are continuously produced by solar ultraviolet light falling on the nitrogen-methane atmosphere. These small particles absorb solar radiation and account for the deep brownish-red tint. The haze particles are thought to settle slowly through the atmosphere and accumulate on Titan's surface. The amount produced throughout the history of Titan is calculated to be the equivalent of a continuous layer of organic solids covering the entire surface to a depth of at least hundreds of meters. Titan's atmospheric chemistry and the presence of complex organic compounds suggest that the Moon may be a laboratory for studying the types of organic molecules and the chemical processes that led to the origin of life on Earth 4 billion years ago. Titan's nitrogen-rich atmosphere is thought to be not primordial but rather a secondary atmosphere like Earth's. It probably arose from photochemical dissociation of ammonia, an abundant ice in the outer solar system, into molecular nitrogen and hydrogen. The ability of a large moon such as Titan to subsequently retain a substantial atmosphere for billions of years depends on a delicate balance between surface gravity, atmospheric molecular mass, and solar heating. The higher the force of attraction between the Moon and an atmospheric molecule, the longer the molecule is retained. On the other hand, the hotter the atmosphere, the more likely it is that the molecule will be lost to space. Jupiter's Galilean moons and Earth's moon are too warm to have retained any abundant gases, but cold Titan and warm but sufficiently massive Earth both have retained the nitrogen molecule. Neither Titan nor Earth has retained the lighter hydrogen molecule. Seasons. Because the declination of the Sun in Titan's sky changes over a range of nearly 60 degrees throughout the Saturnian year of nearly 30 Earth years, Titan is expected to exhibit seasonal changes in its atmosphere and on its surface. During the main Cassini mission in 2004 to 2008, which occurred in the southern hemisphere's summer, more clouds and lakes were observed in the northern polar regions, where it was winter. Clouds in the temperate zones were observed only in the southern hemisphere. There were indications that this situation would reverse, at least in part, as an equinox approached in 2010 and clouds in the northern temperate zones appeared for the first time. Surface. Titan's surface, like Earth's, is sculpted by wind and probably also rain, in the form of liquid methane. River channels coated with dark hydrocarbon deposits are common, sometimes running along faults and sometimes with extensive tributary systems. Thus, the role of methane on Titan may be similar to that of water on Earth. That is, it may be the principal agent behind erosion processes. The equatorial and temperate regions of Titan have vast areas of dunes formed by wind-blown sand rich in organic compounds. The Cassini spacecraft discovered an extensive system of lakes filled with liquid hydrocarbons in the North Polar region. Reflections of the sun have been observed on the lakes that confirm that they are filled with liquids rather than ice or sand. Size and distance. Titan has a radius of about 2,575 kilometers and is nearly 50% wider than Earth's moon. Titan is about 1.2 million kilometers from Saturn, which itself is about 1.4 billion kilometers from the Sun, or about 9.5 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. Light from the Sun takes about 80 minutes to reach Titan. Because of the distance, sunlight is about 100 times fainter at Saturn and Titan than at Earth. Orbit and rotation. Titan takes 15 days and 22 hours to complete a full orbit of Saturn. Titan is also tidally locked in synchronous rotation with Saturn, meaning that, like Earth's moon, Titan always shows the same face to the planet as it orbits. Saturn takes about 29 Earth years to orbit the Sun, a Saturnian year, and Saturn's axis of rotation is tilted like Earth's, resulting in seasons. But Saturn's longer year produces seasons that each last more than 7 Earth years. Since Titan orbits roughly along Saturn's equatorial plane, and Titan's tilt relative to the Sun is about the same as Saturn's, Titan's seasons are on the same schedule as Saturn's seasons that last more than 7 Earth years, and a year that lasts 29 Earth years. Origin. Scientists aren't certain about Titan's origin. However, its atmosphere provides a clue. Several instruments on the NASA and ESA Cassini-Huygens mission measured the isotopes nitrogen-14 and nitrogen-15 in Titan's atmosphere. Surface. The surface of Titan is one of the most Earth-like places in the solar system, albeit at vastly colder temperatures and with different chemistry. Here it is so cold, -179 degrees Celsius, that water ice plays the role of rock. Titan may have volcanic activity as well, but with liquid water, lava, instead of molten rock. Titan's surface is sculpted by flowing methane and ethane, which carves river channels and fills Great Lakes with liquid natural gas. No other world in the solar system, aside from Earth, has that kind of liquid activity on its surface. Vast regions of dark dunes stretch across Titan's landscape, primarily around the equatorial regions. The sand in these dunes is composed of dark hydrocarbon grains thought to look something like coffee grounds. In appearance, the tall, linear dunes are not unlike those seen in the desert of Namibia in Africa. Titan has few visible impact craters, meaning its surface must be relatively young, and some combination of processes erases evidence of impacts over time. Earth is similar in that respect as well. Craters on our planet are erased by the relentless forces of flowing liquid, water, in Earth's case, wind, and the recycling of the crust via plate tectonics. These forces are present on Titan as well, in modified forms. In particular, tectonic forces, the movement of the ground due to pressures from beneath, appear to be at work on the icy moon, although scientists do not see evidence of plates like on Earth. Atmosphere. Our solar system is home to more than 150 moons, but Titan is unique in being the only moon with a thick atmosphere. At the surface of Titan, the atmospheric pressure is about 60% greater than on Earth, roughly the same pressure a person would feel swimming about 50 feet or 15 meters below the surface in the ocean on Earth. Because Titan is less massive than Earth, its gravity doesn't hold onto its gaseous envelope as tightly, so the atmosphere extends to an altitude 10 times higher than Earth's, nearly 600 kilometers into space. Titan's atmosphere is mostly nitrogen, about 95%, and methane, about 5%, with small amounts of other carbon-rich compounds. High in Titan's atmosphere, methane and nitrogen molecules are split apart by the sun's ultraviolet light and by high-energy particles accelerated in Saturn's magnetic field. The pieces of these molecules recombine to form a variety of organic chemicals, substances that contain carbon and hydrogen, and often include nitrogen, oxygen, and other elements important to life on Earth. Some of the compounds produced by that splitting and recycling of methane and nitrogen create a kind of smog, a thick, orange-colored haze that makes the moon's surface difficult to view from space. Spacecraft and telescopes can, however, see through the haze at certain wavelengths of light outside of those visible to human eyes. Some of the heavy, carbon-rich compounds settle to the moon's surface. These hydrocarbons play the role of sand in Titan's vast dune fields. And methane condenses into clouds that occasionally drench the surface in methane storms. The methane in Titan's atmosphere is what makes its complex atmospheric chemistry possible, but where all that methane comes from is a mystery. Because sunlight continuously breaks down methane in Titan's atmosphere, some source must be replenishing it or it would be depleted over time. Researchers suspect methane could be belched into Titan's atmosphere by cryovolcanism, which is basically volcanoes releasing chilled water instead of molten rock lava, but they're not certain if this or some other process is responsible. Potential for life. The Cassini spacecraft's numerous gravity measurements of Titan revealed that the moon is hiding an underground ocean of liquid water, likely mixed with salts and ammonia. The discovery of a global ocean of liquid water adds Titan to the handful of worlds in our solar system that could potentially contain habitable environments. Additionally, Titan's rivers, lakes and seas of liquid methane and ethane might serve as a habitable environment on the moon's surface, though any life there would likely be very different from Earth's life. Thus, Titan could potentially harbor environments with conditions suitable for life, meaning both life as we know it, in the subsurface ocean, and life as we don't know it, in the hydrocarbon liquid on the surface. Although there is so far no evidence of life on Titan, its complex chemistry and unique environments are certain to make it a destination for continued exploration. Why we study Titan. Titan is Saturn's largest moon, nearly the size of Mars, but it's more than just a moon. It is a laboratory for life unlike anything we see on Earth. In a strange way, Titan may be the most Earth-like world out there. It is the only other place we know of that has liquid on its surface, but in Titan's case the liquid is mostly methane, which fills up seas, flows in rivers, and even rains down from the sky. It's so cold there that the mountains and valleys are sculpted from water ice as hard as stone. But if humans were to journey to Titan, we wouldn't need the bulky pressure suits that astronauts wear for spacewalks. That's because, despite the moon's weak gravity, the atmospheric pressure near its surface is about 60% higher than on Earth. It is the only moon in the solar system with a substantial atmosphere. The atmosphere is mostly made of nitrogen with a small amount of methane, but near the top of the atmosphere, high-energy particles and radiation from the sun split these atoms apart. Their constituent parts react with one another to form a thick orange haze. Carbon-rich compounds called tholins snow down from the haze onto the moon's surface, building up huge dune fields in the flatlands. These tholins could be the building blocks of life, if it is possible to base life on liquid methane and ethane instead of water. If there is any liquid water on Titan, it must be buried deep beneath the frigid surface, hidden in impact craters, or erupted by strange, icy volcanoes. Because the primary surface liquid there is methane, one might expect any life that evolved there to be methane-based just as Earth life is water-based. It's not clear that Titan could host any living organisms, but the liquid on its surface makes it one of the most promising places in the solar system to look. If there are signs of life there, it could be the key to understanding what ingredients are necessary for life to evolve and how it arose on Earth. It could tell us whether we should expect any life we find anywhere in the cosmos to be Earth-like, or we should discard all expectations and be open to the possibility of life vastly different from anything we've seen before. Missions to Titan. Titan's thick atmosphere makes it extraordinarily difficult to study from afar. To most of our telescopes, it looks like a fuzzy orange ball. Before we sent the first spacecraft to study Titan up close, that opaque haze led many astronomers to believe it was the largest moon in the solar system, a title actually held by Jupiter's moon Ganymede. The first three missions to visit, Pioneer 11 and Voyager 1 and 2, could not penetrate the haze, leaving Titan's surface a mystery. Infrared light could pierce the atmosphere, so some images from the Hubble Space Telescope revealed vague areas that were brighter or darker than others, but it wasn't entirely clear what those areas were until the Cassini mission. The Cassini mission orbited Saturn from 2004 to 2017, and in that time it gave us nearly all of the information we have about Titan. It had infrared and radar instruments that allowed planetary scientists to see all the way to the huge moon's surface during 127 flybys, and it also carried the Huygens probe. Cassini dropped Huygens through the haze to Titan's surface, where it made the most distant spacecraft landing ever. It took valuable atmospheric data as it fell, and sent back pictures from Titan's surface once it landed. Now that we know about Titan's methane seas and chemically complex atmosphere, NASA is preparing to take the exploration of this strange moon one step further with the Dragonfly mission, scheduled to launch in 2027. Dragonfly is a small drone designed to cover more ground than a traditional lander or rover by making short flights around Titan's surface. Its main goals are to figure out whether Titan is, or ever has been, habitable, look for complex chemistry, and even check if there are signs that this hazy world has actually hosted life.
Whether life exists on Titan is still a mystery, but the possibilities are there.